The Mediterranean Sea has been very, very hot lately. Some up to 5°C hotter than historical averages. Why is that? Why does this happen? Well, new research reveals the spark that ignites Mediterranean marine heat waves. Hello, friends. Jim here. Okay, let's take a look. The Mediterranean Sea is particularly susceptible to marine heat waves, such as the record-breaking 2022 heat wave, which was characterized by anomalously high sea surface temperatures due to the interplay of air-sea heat fluxes and local oceanographic processes, leading to significant impacts on marine systems and coastal communities. A new study led by CMCC brings the scientific community one step closer to identifying the driving forces behind these events. And that's the Center on Climate Change, right? Analyzing over hundreds of marine heat wave events identified through advanced satellite data and clustering analysis, the study appearing in Nature Geoscience shows that persistent subtropical ridges, which are intrusions of warm air from over the African continent into Europe, often informally referred to as African anticyclones, do far more than simply raise air temperatures. Now, since the Mediterranean Sea is in the northern hemisphere, okay, an anticyclone will have a clockwise flow. While subtropical ridges occur frequently in summer, about every 2 days, their persistence is what creates the critical conditions for marine heat wave formation. During marine heat wave onset, ridge occurrence becomes persistent. The high-pressure system associated with the ridge becomes stationary, disrupting the normal eastward movement of weather system. So basically, it's blocking. It just blocks airflow or system movement. When these ridges settle over the Mediterranean basin for 5 consecutive days or more, they cause the prevailing winds to still, which then leads the sea to stop shedding heat and surface waters warm rapidly. Because if the air is moving, it allows the heat to be whisked off the surface of the sea. Think of evaporative cooling, right? You get a nice hot day, you get a nice breeze, it pulls the heat off your skin. No wind, and the heat becomes oppressive. And if you couple that with whatever the humidity is, it becomes extremely uncomfortable. Well, if there's no movement of air, it's not going to pull the heat from the ocean. You're not going to get that evaporative cooling. Allows the waters to warm up. Our study identifies the favorable conditions leading up to marine heat waves and reveals that they are triggered by persistent subtropical ridges which weaken strong winds in the area. There's your mechanism. The findings demonstrate that 63.3%, 46.4%, and 41.3% of marine heat waves in the western, central, and eastern Mediterranean, respectively, occurred during periods when, with both subtropical ridges and reduced wind conditions. A remarkable concentration, considering these combined conditions, only occurred during 8.6% to 14.6% of all summer days. But apparently, it's enough. When subtropical ridges persist for several days, the resulting decrease in wind speeds cause a substantial reduction in heat loss from the ocean to the atmosphere. This heat loss accounts for over 70% of the total heat flux in affected regions and drives the majority of the ocean temperature change. It is very satisfying to identify the mechanics behind a phenomenon we have been studying for years, says lead author Giulia Bonino. Furthermore, likelihood ratios across 3 Mediterranean clusters, 26 events in the Western Med, 18 in the Central Med, 14 in the Eastern Med, reveal that when a subtropical ridge and weak winds strike together, a heat wave is 4 to 5 times more likely to form. The discovery of this statistical relationship provides the foundation for more accurate prediction systems that could help protect vulnerable marine ecosystems and dependent industries from future extreme events. For example, in the Gulf of Lyon, subsurface temperatures climbed by almost 7 C over just 2 days during the most extreme events, illustrating the dramatic speed at which marine heat waves can develop and the need for accurate predictions and effective responses. So by combining the subtleties of meteorology with high-resolution ocean data, the team shows that early warning systems can move beyond temperature thresholds to embrace the physics that actually triggers an event. With Mediterranean seas warming faster than the global average, knowing with accuracy when a marine heat wave is about to strike is essential and important. And of course, having such results helps improve forecast systems and Earth systems models, etc., etc. Now, a couple things I want to say. Notice there's no mention of aerosols. Okay, I had to get that out of there. But right here, this heat loss accounts for over 70%. In other words, heat loss accounts for 70% of the total heat flux in affected regions. In other words, those factors there, the ridge, right? The ridge and the weakening winds, they explain 70% of the variability of the response, which is the ocean's heating up. So when you get 1 or 2 variables that explain 70% or more, you have the main factors. So no doubt they perform some statistical analyses, regression analyses, and determine those 2 variables to be the main drivers. Why is this important? Well, for obviously for the Earth system modeling, so on and so forth. But remember what I have said numerous times. When the Mediterranean water exits through Gibraltar, even though it's hot, it has a high salinity, about 36 or more. So it may be hot, but the salt makes it dense to the point where it will sink down to about 700 to 1,000 meters in depth, becoming the North Atlantic intermediate water. It flows out Gibraltar, sinks to that depth. The main flow is acted on by Coriolis, which moves it to the right and aims it right for the Fram Strait. Mediterranean water goes into the Arctic Ocean through the Fram Strait. And that brings lots of warm water into the Arctic Ocean, as well as a high salinity account, so that there is a salinification, if you will, of the Arctic Ocean. Not a freshening, but an increasing saltiness to the Arctic Ocean. So, and then of course what happens in the Arctic doesn't stay in the Arctic. The Arctic is warming overall 4 to 5 times faster than the rest of the planet. And we have what? The Mediterranean Sea itself is warming a lot higher than other regions of the oceans. Sometimes up to 5 degrees C more so. It would almost seem like there's a direct connection there, or a strong contributing factor there between the Mediterranean, the Arctic Ocean, and then the rest of the planet. As the Arctic warms up by such great amounts, that affects at least the rest of the hemisphere. And we all know what's going on in the Arctic. Lots of sea ice, permafrost thaw, etc., etc. So, this is important because we now have a mechanism identifying why marine heat waves in the Mediterranean take place. I wanted to bring that to you. Thank you for your time. We'll talk soon.